Okay, my name is Dierk Ohlerich, and I'm Chaos from Farbrausch, better known as Chaos from Farbrausch, or the product. And I'm talking a little bit about 3D engines. When you're doing your 3D engine by your own, with your own hands, you're not using some middleware, which is absolutely strange in the demo scene, then you will most likely have quite a lot of code like this. This is in this example is DirectX with all these setting up some system calls, and the unhappy thing about code like this is it's unreadable, it's ugly, it is hackish, no fun, and a lot of possibilities to introduce errors into this code. And what would be much better is to have some kind of layer of abstraction between all the nasty details of the 3D API and your daily work, programming effects and cool stuff. And the whole idea of introducing a layer of abstraction is to have that layer of abstraction less general and more limited than the underlying API. Because if you would create something as general as the API, you could use the API in the first place. It won't help you much. But if you concentrate on the features from the API that you need and build your own little wrapper functions which do the things simpler, smarter, and more productive, then you are more productive. And when I said you are leaving something out, you're making it less general. The good thing is these small wrapper codes you write, you have written them on your own. So when you see that you need more features, you just implement them, and then you have them. You don't need to be too general in your first try. You just make it simple and add all the things you need, and not the things you might need in 2 years. And so I think every 3D coder who does some real hands-on work on 3D engines has its own favorite data structures that have grown with him. And I wanted to talk a little bit about the data structures I developed over the past years. I shaped, and I've been writing many engines on many different platforms. I've been writing for all kinds of PCs, for PlayStations of different kinds, even for phones and stuff. But I found always some data structures that I use all the time and that are my favorite ways of coding. And I want to share them. Specifically, it's my material structure, my geometry structure, and my paint job, my beloved paint job. It's not specific structures, it's just ways of doing things. Each engine I write has a different implementation of these, but the general ideas are always very similar. And we start with what I call the material structure. And whenever you're doing direct 3D API code, you will have this whole bunch of states. You will setting states all the time. My worst remembrance is trying to program a register combiner in OpenGL. It was pages full of lines with just setting states. And well, this is something we can simplify a lot, make more convenient for you as an effect programmer. Have some kind of material structure with all the flags and nice structures. We have here, in one line, I can set on the set buffer, it should be, culling, set the culling on, and maybe switch the fogging on. I can all write it in one line, put it in the flags, and the material will care for all the set render states which lie behind the simple line. The same thing is with textures. I can just write a few lines, and I have the texture with the right setup. And as I said, we must limit it. It would be simply stupid to have a structure like this that can hold every possible OpenGL or Direct 3D state. By a careful selection of states, we can make a very convenient way of setting materials. Just think, what are the things you usually need? What are the things you usually don't need? We can combine things. For instance, for switching on alpha blending, we would have to program 3 or 4 states. We can just say material alpha blend, and then it's alpha blended, and all the states will be set. Or we can see material blend add, and it will be an additive blending. That would be much more convenient to use. You can give if you are working with artists and writing user interfaces to artists, as we in Farbrush usually do it, you can turn this selection of useful states into a user interface with some checkboxes and stuff. Again, I've seen such user interfaces which simply put all the OpenGL state names in the interface. And that is extraordinarily useful for an artist to travel with OpenGL states. It's much better to have this selection, find good names for it, and let the artist go with it. Anyway, you will change this very often. You might find specialized materials for special engine setups, for special effects, and it might be a good idea to plan this in a versatile way, so that you can exchange the material structure without rewriting your whole code. Maybe have several different materials in parallel, maybe make it virtual or something. Because this is something you will change a lot, I think. So now we have this material, we have this nice function, but nobody can, well, we have to set the states anyway. And my favorite way of setting the states is to make first a list of states, a list of tokens and values. And depending on my nice named flags, I just put all these states into a big buffer, a big list, to be handled later. And this preparation doesn't have to take place every frame, because I want to have high performance and I don't want to lose a single cycle. So I just do it once before I paint the material. Then I have this list. And once I have this list, okay, I have this list, and this code that creates the list can be pretty large. I have seen this routine being 2 or 3 kilobyte long, and if you're coding intros, you can just keep it out of your code, put it in the tool, only saves the generated list. And this list packs pretty well. Almost everything can be fit into 8 bits. Values, almost all values fit in 8 bits, almost all tokens fit in 8 bits. You can arrange the bits in a ways. And once we have the small list of tokens, you can do all the crazy compression techniques. There are like reordering them, sorting them, doing the transpose of the whole array. This all can get you a pretty compact representation of all your states. And once you have this compact representation, or if you don't care for size, just if you have the list, you can have one single routine that handles all your nasty state sets, which just iterates through the loop, fetches a token, fetches a value, and then, depending on the token, calls the respective routine to set the state. I have encoded the texture number in the higher bits and the texture state in the lower bits. Another good thing is, as we have all state sets in one small tiny loop, we can easily add state filtering. Usually it is really difficult to make sure that you don't call set render state too often, because it's just unnecessary overhead to call it, although the state doesn't change. Actually, most of the states never or seldomly change. But you have to set them just to be sure. And with this simple state filtering, you can make sure that you get rid of 2/3 of all render state calls, just with 2 lines of code. So this is what actually happens every time I set a material. I have this loop that sets all the things, and this is everything that has to be done. And small loops are good for optimization. You can just, you have a cache-compatible thing. You have state filtering. With OpenGL, there are more different functions you have to call for the different states. It might get a bit messy. And, well, what are the states that we have? And I'm now saying, if you're using DirectX and you're using a programmable pipeline, if you're using shaders, not fixed function pipeline, then there are pretty few states that you actually have to care. There's these render states, which is just a whole big everything. Then you have the sampler state, which specifically controls how textures are filtered. Then you must set the texture pointer somehow. You have to set the shader and the shader constants. And that's actually all the state information DirectX needs which I think are related to the material. So your set material routine can be pretty small because there's not much to do once you have prepared everything in your prepare code. Actually, I think because there are only so few APIs that you need to learn to get the shader running, as soon as you got your first cube spinning, if you're a beginner programmer, you should directly go to shaders because it's so much simpler to learn shaders than to learn the fixed function pipeline. The fixed function pipeline is totally strange with all kinds of states and materials and light states and all the things. With shaders, you have to program your lights by yourself, but the interface is very small. So we have seen what my definition of a material is. We have lots of states, we have a few textures, and the pixel and vertex shader with their constants. What definitely is not part of this structure is viewports, camera, model, light, all the position, rotation things, metric things that you need to set up to do some rendering. That belongs in other structures. I usually try to keep all animated stuff out of the material because the material is often hidden very deep in other data structures and it's hard to get to them, to animate them. And we also have this prepare thing that you can't be really sure that the variable you're animating is really affecting the next frame. I have actually, most Werkzeug users have to fade in and out light sources if they want to fade in and out materials because it's easy to animate the light source while it's hard to animate a material in my systems. So yeah, this is my material abstraction. So now that we have described how things should look or set up the render states, we need something solid to render. And that's what I call a geometry. It has vertices. We have to connect the vertices to the faces, which is usually the indices. And the common API for passing over geometry to the graphics card are vertex buffers and index buffers. In DirectX, this is the only way you can give data to the graphics card. There's no GL vertex and no GL vertex area in DirectX. In OpenGL, you have many different choices, but vertex and index buffers are becoming much more popular over there too, because they are, from the point of view of the graphics card, the optimal solution. There are two major cases: static geometry and streaming geometry. Static geometry, you create once, draw all over the time. Streaming geometry, the geometry is created immediately before it's drawn for dynamic animated things. And whenever you're arbeiting with vertex buffers, you should keep in mind that you should make them quite big. Not too big, not a gigabyte or something. Just a few megabytes is a good size for them. If you have many small things to draw, you should put all these many small things in one big vertex buffer to just reduce the overhead of creating vertex buffers, of switching vertex buffers. Setting up your vertex buffer becomes quite troublesome if you have all these performance considerations in mind. And that's a good reason to come up with a kind of abstraction. This is my favorite way of loading a vertex buffer. Actually, it's loading vertex and index buffer at the same time. You say, okay, I have a geometry and I want to begin loading it. I have a certain amount of vertices and indexes I want to put there. It's a triangle list, what I'm going to do. It's the static geometry, and this is my vertex format. It's a simple vertex. It doesn't have some kind of texture space or something. And when I call this function, the function will pass me two pointers, the vertex pointer and the index pointer, and I'm just filling up the buffers that this function gave me. This is important. I'm never passing buffers to the graphics card. The graphics driver tells me where he wants my data. And this is why this interface begins with begin load. Okay, I have the pointers, I fill it, then I say end load, and everything is done. And later, then I can draw it. The important idea is that I'm not creating a new vertex and index buffer with each instance of sGeometry. sGeometry is just giving me a slice of the cake. There's one big vertex buffer object somewhere, and when I say, okay, I begin loading, then he tries to add the data to the existing vertex buffer object. If this isn't possible because it just won't fit, it just creates a new vertex buffer object and I start writing to that. This is actually a very simple piece of code. It's just delegating the data to different vertex buffers. And I, as a programmer, can just, well, live with this small code and don't have to care about vertex buffer allocation, putting things together. One thing is, I said, we should make our abstractions limited. Don't put the whole expressive wealth of the API to the user. And for instance, when you're doing a 3D engine, or when you're using a 3D engine, you usually will only need a few selected vertex formats. And then you can just make a small enumeration of these few formats and have your engine layer handle all the descriptors you need to set up to tell the graphics card which vertex format you are using. So this is why I just say vertex simple, because this is just one of 4 formats I usually use, and I don't want to explain it every time in detail. The other important kind of geometry is streaming geometry, where I want to create geometry on the fly for some morphing objects. And exactly the same interface can be used to have the state. I say, this is the amount of vertices I want to use, this is the amount of indices I want to use, it's a triangle, it's streaming. It is a simple vertex, I get my pointers, these point to AGP memory, I just write the data to AGP memory, I say I'm finished, and directly after I said, okay, it's upload, I have to draw. Because this is a streaming geometry, I can't keep it somewhere, I have to draw it immediately. I may be drawing it multiple times, but it must be immediately. So not only the interface is the same, even the code is the same for the implementation. It's only a few ifs in your code. If you're looking for code size, it's always good if you can have such a thing. Again, there's one big dynamic vertex buffer object which is shared among all dynamic as geometry instances. And if there's still space, it just gets appended with the new overwrite flag. If there isn't enough space, I don't create a new one, I just reuse the old one using the discard flag, which is the implementation of this vertex buffer streaming in DirectX at least. I just have to remember that I have to draw immediately, because when I have done end load, and I begin a new load, this new begin load may call discard, and then my geometry has gone away, sent over to the graphics card for it to deal, and I can't just draw it anymore because it's gone. And it's a pretty convenient thing to have your application handle static and dynamic cases similar, because, well, you can reuse code between static and dynamic cases, which is also good. This no overwrite discard method is very error prone. There are many possibilities to do it wrong, and if you do it wrong, you screw up really badly, because it can slip by unnoticed, and the graphics card is doing strange stuff, and you suspect the driver, because the driver is always guilty. And so it's a very good thing to have all this error-prone handling in one central place, one place to make the bug, and when you make a bug, make it big so that you notice. And again, we have this vertex buffer and index buffer handling simultaneously, which is also a very convenient thing. Unfortunately, there are a few minor drawbacks which can all be solved pretty easily. One problem with DirectX is that you can't handle quads directly. You have to create a triangle list with an index buffer which has the right pattern for rendering quads. And this is, when you're doing dynamic stuff, you don't want to do that index buffer in a dynamic way. That would be a waste of performance. So you can pre-create one big static index buffer with the right pattern in it. And then when you say begin load with a special flag saying that you want to send a quad list, this begin load will use the vertex buffer normally, but instead of giving you a pointer to an index buffer, it will use this static pre-created index buffer, and then you have a quad list in DirectX, which is very required for particles, for instance, because particles usually are quads. Another problem with particles is that when you are doing your particle loop, like we have 10,000 particles, you go through the loop, and during going through the loop, and you write the vertex buffer, you might notice that some of these particles passed away. And then in the end of the loop, you will notice that you will have less particles in your array than you originally estimated. And since you gave the vertex count at the beginning, this is a problem with this interface. The simple solution is, of course, that you state a maximum expected count at the begin load, and the exact count you actually needed at the end load. And in this case, the memory isn't really wasted because the next begin load can just continue where you stopped with the end load. The only thing that you might waste is if your estimation is too way off, you might have a few discard calls too much. But well, that's less expensive than going through the array twice, which would be the other solution. So we could have an alternate end load, which states the exact number of indices and vertices again. And with these two enhancements, you can handle particle systems, which are the major application of dynamic vertex buffers and demos, very well. Another problem is there are situations where you can't draw immediately. Dynamic vertex buffers require, or streaming vertex buffers require you to immediately draw your stuff. But if you want to draw something twice, the same buffer twice a frame, at different places of your rendering, then you are in a big problem. But well, the whole concept with begin load and end load is very flexible. You can create a third kind of geometry of dynamic vertex buffers, which are not discarded. Instead, when your dynamic vertex buffer runs out of space, you create a new one and put the data in there. And these buffers are only discarded at the end of the frame, for example. And they are discarded. They are not deleted or destroyed. They are only discarded and reused next frame, of course. This way you can create, for instance, some strange blob object and render it twice in very different phases of your 3D engine if you're doing some multipass rendering or something. But please don't create and destroy any buffers every frame. That would be shameful. Yeah, with all these tricks to do, we have a, I think, pretty nice interface for loading geometry into your graphics card. Easy to use, simple to implement. It's all in all, one or two pages of code, depending on your screen resolution. Buffer management is a very important thing because if you do it wrong, you are either running into performance problems or your application is simply faulty. So it's a good thing to hide it away in one place at your code and yeah, have one place for the bugs, not many. So we have a material, we have a geometry. What can we do with it? We can put them together. And now we're coming to the paint job. A paint job is a geometry, a material, and a matrix for a position of the model. All this together is the what, the how, and the where. This describes a paint job or a batch, the atomic thing that you should pass to a 3D card for rendering. Of course, we will need all small stuff for maintaining lists and stuff. But the basic content of a paint job is the geometry, a material, and the model matrix. And your whole scene consists, you need the camera somewhere, you need to specify screen clearing, you need to specify where to render, like a render target, which is the screen, or maybe a texture. You will have light sources, and a list of paint jobs. And this is this describes a whole scene for rendering. And the most important thing is, of course, the list of paint jobs, because that's the headline of the whole slide, paint jobs. Where did these paint jobs come from? If you have a game, there are many sources for paint jobs. In demos, things are often much more simple, but in games, there will be the huge amount will be static geometry pre-created by the artist. Well, the whole level. This is what comes out of Maya or Softimage or whatever you're using. Then there are special effects from the coders, where they create some particle systems, lens flares, or whatever you need to be hip. Then there will be some head-up display drawing, some gauges and numbers and whatever you need. And of course, moving objects from the game logic. There will be missiles, and each missile will have an object, and it will have special effects attached to it. And these are all different sources for paint jobs. And in the system I usually use in my engines, all these sources for paint jobs just have to call add paint job. And then the paint job is in the list of paint job. What we're doing here is we are deferring the painting. We are not painting immediately. We are first building up a list. Maybe it's because I'm German. I want to make lists of everything. But so we are introducing an overhead here. And if we're introducing an overhead, it should better be good for something. The good thing is that we can reorder, that we can change the order of painting without changing the order of code. If you're just doing a demo with a few effects, you can easily change the order in which these effects are painted. But if you are mixing artist-created static scenery, special effects, and moving objects from a game logic, you don't want to organize your game logic that the painting comes out in the right order for the paint jobs. So it's actually very convenient to have one stage where you see the whole scene and decide how it should be painted. So why are we so interested in the order of painting? There are, of course, two reasons: translucency and performance. For performance, we have to decide, we have to minimize state changes. And we have to find out what the most expensive state change is, and see that we order our paint jobs in a way that this state change is not often. For current engines, the most problematic state usually is shaders. On some consoles, I have big problems with the order of textures. I always sort for textures on consoles. But you actually have to try what makes your engine fast. This is a little bit a black art, less than a science. But performance sorting is not that critical, because if you mess up the performance sorting, then your engine will get a little bit slower, and most likely nobody will notice anyway. Even worse is translucency sorting. If you have transparent layers, alpha blended, additive blended, all that kind of stuff, you have first to paint all the opaque objects and then the transparent objects. And even within these transparent layers, you have to make sure that you are drawing them in the right order to make it best looking. The problem is, if you're doing additive blending, if you say x plus y or y plus x, the order doesn't matter. If you do multiplicative blending, which makes wonderful dark stuff in your scene, then the order doesn't matter too. But if you're doing alpha blending, the order does matter, because you can't simply change it around. It doesn't work. So a naive approach would be to sort all individual triangles. Because then, if you sort them from front to back or from back to front, all the sorting would be in the right direction. But I can only warn for that. The performance of this can be awful. I have in my current game engine some special cases where I have 10,000 of transparent sorted billboards. And that actually works pretty well. But usually it just doesn't work. The biggest problem is that most likely all these translucent triangles don't have the same material. And so if you're sorting them, you would have to change the material for each triangle or for small groups of triangles. And this is disastrous. So, we have to find another solution. And do we really need to sort individual triangles? Maybe all we have to sort are the paint jobs. And this is what I usually do. Each paint job is assigned a number, as a render pass. Opaque paint jobs end up in pass 0. They are painted first. All the other translucent paint jobs get a number from 1 to whatever you imagine your maximum number. And then I simply have to sort the paint jobs. The order in which the paint jobs are registered is of no interest. The sorting is all done by this ordinal number. And we can sort first, of course, by render pass, and then inside a render pass. And the first render pass, the opaque render pass, will be huge because most of your geometry will be opaque. Inside each render pass, we can sort for performance considerations. And well, this is especially useful for artist-generated content because the artist usually has no way of specifying the order of things to draw. But it is extraordinarily useful if the artist has this possibility. I will show you a very old demo we made. I'm not showing you the demo, of course. I'm just showing you the tool. This is FR08. And my favorite scene for demonstrating render passes, or how artists can use render passes, is the trespasser scene. What we see here is many transparent fences. And these are, of course, done with alpha-blended transparencies. And you see all the smooth edges. Fiverr is extraordinarily keen on having here smooth edges. He doesn't want to see any jagged Kanten, edges. He wants to see smooth edges without full scene anti-aliasing, of course, because that isn't usually available at that point of time. And you see all these transparencies are correctly sorted. I can show you how it looks if the sorting is wrong. I just go in a place where the camera will never go. And from here, the sorting is wrong. Whoops. You see here that first he paints the front fence, and then he just leaves this little hole with alpha test for the back fence. This is how things should not look. And of course, we are not sorting individual triangles here. We are just split up the geometry in 3 groups. And the first group is the inner ring, which is painted first. The second group is the inside of the outer ring, that is painted second. And the third group is the outside of the outer ring. And no matter from where I look, it will always look correctly sorted. I'm not pretty good with this camera anymore. It's a very old tool. But there are no sorting errors in the scene. And all this is done without sorting individual triangles. It's just done by carefully splitting the scene into 3 render passes. Actually, it was a little bit sloppy. If you put your camera down here and then look upwards, you see all these errors because he just didn't care about that. It is more important that it looks correctly from upstairs. Where the sorting is correct. And if your artist understands how to use this, he can do incredible things with alpha sorting that have no performance impact at all. It will just always look correct. So much for the generator. Don't think I have time for the second example. So we have these render passes, but there's a problem. I already told that stream geometry must be painted immediately. Unfortunately, sorted jobs are painted later, so this doesn't work. There are some solutions. They are a little bit ugly, but in practice they don't impose real problems. instead of storing the geometry in the paint job, you can store a pointer to a handling routine, which creates the geometry at the right time, just in time for being drawn. Or you can have some flags telling that this is a special case which goes through the ultimate particle loop or something. It's actually the same. Just have your dynamic geometry creation at the right time in your rendering. You can put it to an extreme. You can completely sort everything for your drawing of a screen. You will have in a frame, in a complete frame, you might have multiple scenes with multiple render targets, like subtle texture effects, and then a final put it to the big screen scene. Then each scene will have, of course, multiple render passes, and each render pass will have multiple textures and materials and things you want to sort for performance reasons. Now you can put all the relevant information in one 32-bit word, like having the highest 8-bit a scene ID. In the next 8-bit you have the render pass ID, and in the lower bit you just put in what you find is an important sorting criteria. This can be the texture or the shader, or maybe a set information if you want to do a rough set ordered painting for hierarchical set buffers. And once we have the 32-bit word, you just sort all paint job by this word, and we have all the criteria for sorting encoded in this word. If you're doing complete scene sorting, you will have a special paint job setting up the rendering, something like begin scene, clear viewport or something. This will end up in Renderpass 0. And you might have a special paint job at the end of the rendering, something like end scene or so. This will end in Renderpass FF. And all your normal paint jobs go from O1 to FE, this O1 being the first, the opaque render pass, and then all the transparent passes come later. And again, you just sort by paint jobs, and you get one big list with everything you ever have to draw nicely sorted. I usually use radix sort for sorting because it's ultimately fast and easy to optimize, and the data is optimal for the sort. And a good thing is that you can experiment with many different sorting criteria. You just change a few lines of code, and everything is sorted differently, and you see what are the best performance considerations for sorting. I find this absolutely required for consoles, because in a console you have to do actually the work of the graphics driver, and you have to build lists anyway. On PC, it's not that important to my experience, but I still like to do it, just because I'm a German, I like making lists. So we have seen the material, the geometry, and the paint jobs that puts it all together. We have not seen the viewport, which is obviously required to tell where things have to be painted. We will use some kind of texture class, some kind of environment with lights and whatever. You might want to have some metrics and vector classes. I usually even encapsulate the integer just in case. Nobody knows how many bits it has. But all these together make a nice programmer-friendly abstraction for the rendering, so that you can keep all these API-specific calls out of your application code and have it all hidden somewhere where you can easily maintain it. So someone might ask, where's the code? Can I download it somewhere? And of course you can't, because I usually don't put codes in the internet. The main reason is each engine is different. I have been writing many engines, and in each of these engines, first I got smarter, therefore I do things smarter. And second, each engine has different requirements. And with these different requirements, the things that I need and the things that I don't need change. And so it ends up pretty different with each time I design an engine for an application. And this is what you have to do if you want to go this way. You will have to roll your own thing to fit your own needs. And yeah, I hope this was useful. That was the seminar.